Hi there, in this video we're going to discuss second order differential equations. So I've prepared a series of screenshots. So here's the first screenshot. So second order differential equations with constant coefficients. So what are they? So a second order differential equation with constant coefficients is any equation of the form a d2y over dx squared plus b dy over dx plus cy equals f of x, and a, b and c are constants, and f of x on the right hand side is a function of x. Okay, now how do we solve second order differential equations? So let me explain the methods. So to solve a second order differential equation, we need to calculate number one, the solution to the left hand side of your equation, and the solution to the left hand side is called the complementary function, and we use y suffix cf to mean the complementary function, i.e. the solution to the left hand side of your equation. And number two, we need to calculate the solution to the right hand side of the equation, and that is called the particular integral, and that is denoted by y suffix pi. Okay, so remember, we need to calculate two things: the solution to the left hand side, known as the complementary function, as well as the solution to the right hand side, called the particular integral. Okay, so in order to work out the general solution y will be the complementary function plus the particular integral. So y will be ycf plus ypi. Okay, so if you're given a second order differential equation with constant coefficients, so if you're given the equation of the form a d2y over dx squared plus b dy over dx plus cy equals f of x, okay? Now to calculate the complementary function, so remember, complementary function is denoted by ycf, and remember the complementary function is the solution to the left hand side of the equation. So to work out the solution to the left hand side of your equation, here are the steps, and step number one is we let f of x equal 0. Okay, so let f of x equal 0, and if you let f of x equal 0, your equation becomes a d2y over dx squared plus b dy over dx plus cy equals 0, and name that equation star. You'll see why we do this as we continue with the method. Okay, in step number two, we let y equal capital A e to the power mx. Okay, so we always do this in step two. So y equals capital A e to the mx. Capital A and small m are constants. Okay, so if y equals a e to the mx, we need to calculate dy over dx, the first derivative, and bearing in mind a and m are constants, when we differentiate a e to the mx, we're going to have am e to the mx for dy over dx, and if you differentiate again, d2 over dx squared will be am squared e to the mx. Okay, so in step two, take y equals a e to the mx, differentiate once, so you need dy over dx, differentiate again because we need d2 over dx squared as well. Okay, in the next step, step number three, you put your results for y, dy over dx and d2 over dx squared into star, and remember, star is the equation that we have in step number one. So star is the equation where f of x, the function on the right hand side, is replaced by 0. Okay, so put the results for y, dy over dx and d2 over dx squared into star. Okay, that brings us on to the next step, step number four. So we can cancel capital A, so you can cancel the constants capital A, and since e to the power mx is not equal to 0, we come up with this quadratic equation, am squared plus bm plus c equals 0, and this quadratic is known as the auxiliary equation. Okay, Now, the solutions to the quadratic, so the solutions to the auxiliary equation, determines the form of your complementary function, okay? So, depending on your solutions to your auxiliary equation, we need to select one of these three forms for the complementary function YCF. So, let me go through the three cases. So, in this case, case number one is the case whereby if you solve your auxiliary equation and if you have real and different values for m, so for example, if m1 equals k1 say, and if m2 equals k2 say, the form of your complementary function YCF will be of this type. Capital A e to the power k1x plus capital B e to the power k2x, okay? And capital A and capital B in this form are constants that we need to calculate, okay? So we'll come on to the calculation of capital A and capital B, these unknown constants, very soon. So this is case number one, the case for real and different values for m. Now, moving on to case two. Case two is the case whereby you have coincident values for m. So if you have values for m which are the same, okay? So if m equals capital K, say, therefore your complementary function will take this form. So the form of your complementary function for coincident values is YCF is equal to ax plus b e to the power kx, okay? And once again, capital A and capital B are constants to be found. And the third case, case number three, is the case whereby you have complex values for m. So if your solutions for m are of the form k1 plus or minus k2i, so if you have complex solutions for m, then your complementary function will take the form YCF is equal to e to the power k1x, open a bracket, capital A cos k2x, plus capital B sine k2x, okay? So I want you to take notes that k1 is the real part of your complex number. Now, these three cases, you need to learn these cases. So I went through the three cases for the complementary function YCF. So depending on the solutions to your auxiliary equation, you need to select one of these three cases, okay? Now, in the next screenshot, how do we calculate the particular integral? Particular integral is denoted by ypi, okay? So let me talk to you about the steps involved. Now, the form of your particular integral ypi depends on f of x. So it depends on the function of x appearing on the right-hand side of your second order differential equation, okay? Now, I've constructed a table, okay? And you need to select your ypi depending on the form of your f of x, okay? So in this case, the first case for f of x is if you have a constant for f of x, then you need to select ypi to be a constant also. So if f of x is a, say, where a is a constant, then take your ypi, your particular integral, to be the constant p, and our job is to work out the value of p. So I'll talk to you about how we do that calculation very soon, okay? Now in the second case, if f of x is a linear, so if f of x is of the form ax plus b, where a and b are constants, then select ypi, your particular integral, to be linear also. So select ypi to be px plus q, and our job is to work out p and q, okay? Third case for ypi, if f of x is quadratic, so if your function on the right hand side of your second order differential equation is of the form ax squared plus bx plus c, where a, b and c are constants, then take ypi to be quadratic also. So take ypi to be px squared plus qx plus r, and our job is to work out what p, q and r are, Okay. The next case is the case whereby you have an exponential function for f of x. So if f of x is ae to the lambda x, okay, where a and lambda are constants, okay. Now, depending if the exponential function is repeated when you calculate your complementary function, okay. If it isn't repeated, so if your choice for ypi is not the same as your complementary function solution, then take ypi to be pe to the lambda x, okay. However, if the choice for ypi appears as part of your complementary function, you need to select another form for ypi, okay. So I may explain that example in the next video, okay. And in the last case, the case whereby you have sines and coses as part of your f of x, so if f of x is a sine lambda x or a cos lambda x, or even a sine lambda x plus b cos lambda x, then ypi for all three of these forms is p sine lambda x plus q cos lambda x, okay. And again, our job is to work out p and q, okay. Now, looking back at the exponential case for f of x and the trigonometric case for f of x, the lambdas in ypi comes from your f of x, provided that your choice for ypi is not repeated as part of your complementary function, okay. Now, once you've selected your ypi from the table, so once you've made your choice for ypi in step 6, in step 7, you need to take your ypi and you need to work out dy over dx using your ypi and d2 over dx squared using ypi also, okay? So you need to take, in other words, your ypi choice and differentiate once for dy over dx and differentiate twice for d2y by dx squared, okay? Once you've done that, go to step number 8. Step number 8 is to put the results for y, dy over dx and d2 over dx squared into double star, okay? So remember, the very first slide, when I was explaining the methods, I've named the main equation double star. So you need to substitute the results for y, dy over dx and d2 over dx squared in step number 7 into double star, the main equation, okay? So that is what you need to do for step number 8. And in step number 9, in order to work out the unknown constants p, q or even r, what you need to do is you need to group the terms on both sides of your equation, okay? And then when you equate the coefficients of the like terms, you'll be forming equations in order to help you calculate the unknown constants p, q and r, okay? So again, we'll see this more clearly when doing an example, okay? Now, once you work out p, q and r, the last step is to add your solution to YCF to your solution to ypi, and that will give you the general solution to your second order differential equation, okay? So these are the steps in order to work out the general solution, the solution for y of your second order differential equation, okay? So let's get back to the paper and pen and see this method in action with the aid of an example. So back to the paper and pen. So here is an example. So in example 1 part A, we have the second order differential equation d2 over dx squared minus 5 dy over dx plus 6y is equal to 24, okay? So let's have a quick look at the screenshot. So we've been given a second order differential equation, and remember I've named the main equation double star, okay? So back to the paper and pen. So let's do that now. So let me name this main equation double star, okay? And if we go back to the screenshot, to find the complementary function, okay, YCF, the first step, step number 1, is to let f of x equal 0, okay? So if I go back to the paper and pen, here is step number 1. So our f of x is 24, okay? So in step number 1, if I let f of x equal 0, my equation will then become d2y by dx squared minus 5 dy by dx plus 6y is equal to 0. So I'm going to call that equation star. Now let's go back to the screenshot to see step number 2. Step number 2 is to let y equal ae to the mx. Then we differentiate once for dy over dx, and then we differentiate that twice for d2 over dx squared. Okay? So this step will be repetitive when you do examples involving second order differential equations with constant coefficients. Okay? So back to the paper and pen. So here is step number 2. So we let y equals ae to the mx. So remember, capital A and M are constants. We calculate dy by dx. So that is am e to the mx. And we differentiate again. So d2y by dx squared, when we differentiate again, that's going to be am squared e to the mx. Okay? So that takes us to the next step, step 3. So back to the screenshots. So remember, step number 3 is to put our results for y, dy over dx and d2 over dx squared into star. So remember, star is the equation coming from step number 1. Okay? So back to the paper and pen. So let's put y dy over dx and d2y by dx squared into star. So here is star, okay? So if I do the replacement of the results that we have, d2 over dx squared, we have am squared e to the power mx, okay, minus 5. dy over dx, we have am e to the mx, okay, plus 6. Y is ae to the mx, and that is equal to 0 on the right hand side. So that takes us to the next step. So back to the screenshot quickly. So in step number 4, cancel capital A. Capital A is a constant, remember, and as e to the mx is non-zero, we end up with the quadratic called an auxiliary equation. Okay? So back to the paper and pen. So we can cancel the constants, capital A, and as e to the mx is non-zero, we're going to end up with the quadratic m squared minus 5m plus 6, which is equal to 0. Okay? So this is step number 4. Step number 4 is complete. So let's go to the next step, step number 5. So let's go back to the screenshot. And remember, depending on our solutions for our auxiliary equation, we need to select the case for YCF. Okay? So if we go back to the paper and pen, now here is our auxiliary equation, m squared minus 5m plus 6 is equal to 0. So this is our auxiliary equation. So I can factorise this, and the factors will be m minus 3 and m minus 2. Okay? So we have two values for m. So either m minus 3 is equal to 0, which means m is 3, or m minus 2 is equal to 0, which means that m is equal to 2. So in this case, I have two different values for m. So if we go back to the screenshot, that takes us to step number 5. And step number 5 is to select, remember, one of these 3 cases. Okay? So in this case, I've got different values for m. So there's only one case for different values. That's case number 1. Okay? So if we go back to the paper and pen, I'm going to take this as K1. So I'm going to take K1 to be 3 and K2 to be 2. And it doesn't really matter which one you take as K1 or K2. So that doesn't really matter. Okay? However, the form of your complementary function for different values of m always takes the form of YCF, and that is capital A e to the power. K1 is 3, so it's 3x, plus capital B e to the power. K2 is 2, so 2x. Okay, so remember the form of your complementary function for real and different values for n. So let me remind you in red. So remember YCF is A e to the K1x plus B e to the K2x. Okay, so that completes step number 5. Okay, choosing the appropriate YCF. So let me continue on the reverse. So now we need to work out the particular integral. So let's go back to the screenshot. So remember, the form of your choice for YPI depends on what you have for f of x in the main differential equation. Okay, so main differential equation refers to double star. So let's have a look at this table again. So in this case, we have all in all 5 cases. Okay, so we need to select YPI depending on f of x. So if we go back to the paper and pen, our f of x in the main equation double star is 24. So our f of x, in other words, is a constant, it's 24. Okay, so in this case, if we go back to the table, if f of x is a, where a is a constant, then you need to take YPI to be a constant, which I'm calling P. Okay, and our job is to work out P, remember. So back to the paper and pen. So I'm going to take YPI to be P. Okay, so that is step number 6. And that takes us to step number 7. So let's go back to the screenshot. Step number 7 is using our selected YPI, we need to calculate dy over dx and d2 over dx squared. So back to the paper and pen. Our YPI is P. So if we work out dy over dx of our YPI, so bearing in mind P is a constant, when I differentiate, we're going to get 0 for dy over dx. And we also need d2y by dx squared. So if I differentiate 0, it's 0 again. Okay? So let's have a look at the screenshot to remind ourselves of the next step. Step number 8, remember, is to put our results for y, dy over dx and d2 over dx squared into double star. Okay? So remember, double star is the main equation that we had in question. So if we go back to the paper and pen, our double star, the main differential equation that we have is d2 over dx squared minus 5 dy over dx plus 6y equaling 24. So we need to put our results into double star. So let's do that. So in step number 8, so let's put y dy by dx and d2y by dx squared into double star. So if we put them into double star, let's see what we have. So d2 over dx squared and d2 over dx squared is 0. Okay. Minus 5 dy over dx. So minus 5 and dy over dx is 0 also, okay? Plus 6 and y, so plus 6 and our y is p, and that is equal to the right hand side, which is 24. So that is equal to 24, okay? And in step number 9, we need to work out p, q and r, okay? So in this case, let's go back to the paper and pen. So if I simplify, 6p is equal to 24, okay? Which means that p is 24 divided by 6, which is 4. So that is our constant p, okay? So once you have your constant p, so put that into your ypi. So therefore, your ypi is 4 in this case, okay? So that takes us to step number 10. So back to the screenshot quickly. And in step number 10, we need to add what we had for YCF to what we've got for YPI. So in this case, so this is step number 9 done. Here's step number 10. So in this case, our general solution for y is equal to, so remember it's YCF plus YPI. So YCF, let's remind ourselves, we had AE to the power 3x plus BE to the 2x. So let's note that AE to the 3x plus BE to the 2x plus YPI, and we had 4 in the earlier step, okay? So that is the general solution to our second order differential equation that we have for example 1a, okay? So that completes this example. These are the steps in order to work out the general solution for a second order differential equation with constant coefficients, okay? And yeah, let's try another example. So